Good afternoon everyone, my name is Alana and today I will be presenting my final CFM project, which is the modelling of 2D channel flow past a cylinder using the lattice-Boltzmann method. Flow past a cylinder is a well-studied computational fluid mechanics problem where the analytical solution is available for low Reynolds number. Therefore, this simulation can be validated with the literature. Figures on the right show flow past a cylinder for various Reynolds numbers. The objectives of this study are to implement the lattice-Boltzmann method for flow around a cylinder, to investigate velocity boundary conditions at the inlet as well as the outflow boundary condition at the outlet, to investigate the spatial accuracy of the scheme employed, and to benchmark the numerical solution against values in the literature. The lattice-Boltzmann method is based off the Boltzmann transport equation given here, where f is the particle distribution function. On the right-hand side, the collision term is modelled using the BGK operator, which says that the distribution function approaches an equilibrium, which is based on the relaxation time related to the viscosity of the fluid. The macroscopic properties, density and velocity, are computed by summing the moments about the distribution function. The lattice-Boltzmann method occurs in two steps. In the collision step, the particle distribution relaxes towards equilibrium, accounting for particle interactions, and in the streaming step, these distributions propagate to the neighbouring lattice nodes. A D2Q9 lattice is used for this simulation. This figure shows the computational domain that's investigated in this project. For the inlet, a prescribed velocity condition is used, such as that proposed by Zhao and He. In the x direction, there is the analytical solution to Hagen-Poiseuille flow, and in the y direction, there is no velocity. In order to satisfy the number of equations and the number of unknowns, an additional equation which says that the non-equilibrium part of the distribution function that's normal to the boundary is equal to one another. For the cylinder and for the wall on the top and bottom of the domain, a halfway bounce back boundary condition is implemented. The investigation of the outflow boundary condition is currently investigated in the literature. There is often issues such as information from pressure and density waves travelling backwards into the domain due to the nature of the lattice-Boltzmann solver. Here you can see in the red solution where the domain stops at 250 does not match exactly when the black solution where the domain stops at 400. This is due to the backpropagation of information. 3 different outflow boundary conditions are investigated as part of this project. The first is the non-equilibrium bounce back condition, which is the same as that used for the inflow. This works well when the length of the channel is much greater than the height and you see that the velocity in the y direction equals 0 at the exit. Otherwise, the velocity condition is unsatisfied at shorter domains. The second method is the modified extrapolation method proposed by Junk and Yang in 2011. Here you extrapolate the macroscopic properties, density and velocity at the boundary. Lastly, the do-nothing method proposed by Haywood et al. In 1996 is used. This is easy to implement as you assume the distribution function at the exit is equal to that of the nearest neighbouring lattice within the domain in the direction of the flow. However, the one problem with this is that you do get interference between the no-slip boundary condition and the do-nothing method at the top and bottom corners, which lead to this checkerboarding. These videos show the results of the simulation at a Reynolds number of 200 and a Reynolds number of 20. Looking at the top figure first, you see some backpropagation of the pressure waves into the domain. However, after a time, this is absorbed by the domain and you get a steady solution where you have oscillation of the wake and a von Karman vortex shedding. For a Reynolds number of 20, the solution shows a steady state profile. This figure further shows the solution for a Reynolds number ranging from 10 up to 320. It can be seen that after a Reynolds number of 40, you do get to see an uneven distribution across the cylinder in the y direction. To evaluate the accuracy of the solution, the force on the boundary of the cylinder is computed using the momentum exchange procedure. This computes the difference between the distribution functions across the boundary. It's compared with the literature values for the coefficient of lift and the coefficient of drag and can be seen in these two figures. For the coefficient of drag, values from the literature are chosen as reference. The coefficient of lift is expected to be 0 at this low Reynolds number, and so it's just showing the error between that and 0. In conclusion, the lattice-Boltzmann method was successfully implemented for flow past a cylinder, as well as investigation of the boundary conditions at the inlet and exit. This was compared for a range of Reynolds number, and the spatial accuracy of the numerical scheme was evaluated. Recommendations for future work include extending the method to implement an immersed boundary condition for better representation of the cylinder, and investigating the frequency of von Karman vortex shedding to analyse the wake dynamics. Thank you very much for your attention. Here are the references used in the presentation, and I welcome any questions.